at 13th of October. So just to start the day, just want to say thank you everyone for joining this special issue on the International Disaster Risk Reduction Day. So coming to a very brief background to our speaker as well as our attendees who are coming from different academic centers and academic institutions regarding the Center for Disaster and Mitigation Center. Center for Excellence in Disaster Mitigation and Management Center, it started in 2006 at IIT Roorkee. It has been focusing on to make the resilient society with a strong emphasis on techno-managerial skills. The founding head of this center was Professor D.K. Paul. And our center has been really working on a very interdisciplinary research criteria, focusing on different cross-sectoral research, focusing on major areas of disaster in terms of landslide, flooding, earthquakes, as well as the other chemical hazards which are happening in industrial disasters. So what we have been focusing on to see the core area of disasters, plus also want to see the disaster management from the 4 different pillars from the disaster management side, starting from the preparedness, resilience, risk assessment, and mitigation. So very well connected to our center holistic view of managing the disaster. So one of the area where Professor Noy is going to talk about the disaster economic and how it really affects the society and the overall economic of the area which gets affected by disaster. So we're really fortunate to have Professor Noy. Our center vision has been to develop a center in terms of premier center for disaster mitigation and risk management for sustainable habitat. And the mission of our center has been to develop our human resource development for disaster mitigation and management to protect the people, environment, and economics of our society. And that has been done through different educational, our PhD programs, research, and development. Just to give you a brief background of our center has the PG program. We have been giving the Masters in Disaster Mitigation and Management, as well as the PhD in Disaster Mitigation and Management. We have right now around 25 students for the master's program. They are pursuing their first year and the second year research part in the master's program. And we also have around 25 plus research scholars, PhD students who have been working on different research in the disaster site. So starting from the core science in the earthquake, the floods, the remote sensing GIS application in the disaster management, as well as the managerial side, where we are students have been developing a lot of decision support system to manage and to see how the disaster information get disseminated to the community. Our center has been really fortunate to really develop the first of its kind earthquake early warning system for India, especially focusing on this right now for the Uttarakhand state where we are located. And this earthquake early warning system have been funded by the state Disaster Mitigation Management Department, SDMA. And we have been other research projects which have been focusing on the glacier lake outburst, GLOFs, as well as our faculty and the researchers have been working on various aspects of the disaster management. So with this, a few words from our disaster side, from our center side. At this time, I would like to again welcome everyone for this first lecture of this International Day for Disaster Risk Reduction. And I'll request Professor Subir to introduce our first speaker. Thank you.
Thank you, Professor Sen. And once again, I welcome all participants. And now it's my turn to welcome Professor Noy to this lecture. It is really tough to sum up Professor Noy's achievements in 5 minutes. And those of you who are interested to look at his CV, you can go to his nicely, presented information in his website for all the details. I would like to highlight, few things just to, introduce today's speaker, and also that how he is contributing in the field of economics of disaster, which is completely a niche area. Anyone who wishes to work in the area of economics of disaster will come across several of his papers. And he has close to 100 or more than 100 publication, if I'm not wrong by this time. He has guided more than 40 PhD scholars, and he has received many awards. But what fascinates me about his journey into academia is that he has been a tour guide in India, Nepal, and China. So I think, spending time almost 2 years and venturing different parts of this particular subcontinent, I think also is reflected in his writing, that he is so clear about the systems that we have over here, the kind of geography that is there in this part of the country. So that familiarity actually comes up, when you read his papers, and they can be read by anyone. And also in terms of reach and scope of his work, he works in the domain of disaster, he works in the domain of climate change, and of the very few people who actually started looking at CCA and DRR, that is climate change adaptation and disaster risk reduction in the same lens. Now we are talking about unification. He already has contributed in this direction long back. He works in the area of pandemics, and also the fiscal impacts of disaster. I don't know what kind of effects it will have, especially on developing economies. There are a couple of papers of his on Vietnam that will be really very interesting, and anybody wishing to know what will happen for India and other developing countries, that can be a benchmark paper. He has also elaborated on financial crisis, which is also aided area. I believe that is the area of his PhD thesis as well. Currently he is the chair professor in the economics of disaster and climate change at the Victoria University of Wellington in New Zealand. And he is also editor and I think one of the co-founders of the Springer Journal Economics of Climate Change and Disaster. And and there are many other things that you will come across in his CV, but I just wanted to highlight some of them. And regarding awards and scholarship, I would like to mention that in 2019 he was given the International Society for Integrated Disaster Risk Management IDRIM Distinguished Research Award. So that is again something that is directly related to the disaster. So I will not come in your come in between the lecture now, and I request Professor Noy to please start his presentation. Once again, welcome you to IIT Roorkee, and we are looking forward to your lecture, sir. Thank you.
Namaste, everyone. Professor Sumitsen, thank you very much for inviting me. Professor Subirsen, thank you very much for talking to me over the last, I think, maybe 4 years about this topic, and sending some PhD theses my way to examine and collaborate on. So thank you very much for the invitation. I do need to apologize. This is not a lecture about India. Unfortunately, the last project I did in India was started in the Sundarbans, and I was there in just February last year, just when COVID started to rear up its head. And sadly, that I haven't been able to go back to the Sundarbans since, for obvious reasons, and the project has sort of been put on hold because because it's difficult to do these kind of projects when the world is under such turmoil, and also because I sort of veered a little bit to looking more at pandemics in the past year and a half for obvious reasons. In any case, this today is not a lecture about pandemics, although I would be happy to come back in the future, maybe in person to Roorkee and give a lecture about pandemics, hopefully once this pandemic is over. But this is indeed a lecture that tries to connect the idea of climate change and extreme weather events, so disasters, and trying to link them together through what we call climate change attribution. You can see my slides, yes? Yeah, so I think that the first thing to note is when we think about climate change, so there is, let's say this is a distribution of rainfall. We know that the distribution of rainfall is changing, moving to the right in most places, because the oceans are warming, there's more humidity in the air. But the main point that we need to observe is that the big issue with this changing distribution or shifting distribution of rain is that the extreme events, so the very high rainfall events, are going to become a lot more frequent than they were before. So if you look at the black triangle, so that's the amount of extreme rainfall events that happened before climate change, and the red one is with climate change, then you can see that the red one, of course, is much bigger than the black one. And this is the big issue with climate change. That's my contention. So not only is the distribution shifting, we also see that now, because of that shifting distribution, we have those extreme events that we have never seen before. Okay, so that now little red triangle there are those kinds of events, extreme rainfall, extreme temperature, that we have never experienced before. And to make matters worse, we now have also, in most places, the distribution is not only shifting to the right, it is also flattening. And because of that flattening, we see even a bigger increase in the extremes. So again, extreme heat or extreme rainfall. Okay, and not only that, we now can see, for example, here, so we can see with just a one standard deviation shift in the rainfall and a flattening, we see that events that used to be maybe 3-4 standard deviations from the mean are now much more common. Okay, and we've seen that, and I think that discussion has been happening maybe only in the last couple of years, where we have seen these extreme events globally, including in India, but not only in India. And those are events that we haven't really seen before. So we've seen, for example, just this year, we've seen these very extreme heat events in Russia, in Siberia. We've seen an extreme weather event in Canada and the Western United States, extreme heat. We've seen the floods in Europe. There have been floods elsewhere as well, including in New Zealand. So we've seen these events that we have never really experienced before, and we now understand, of course, that this is because of climate change. So what do I want to talk about here? I actually want to talk about a very specific event, and forgive me, but I'm focusing on an event from the United States, and I'm specifically Hurricane Harvey, which happened in August 2017, so about 4 years ago. So this was, as the president at the time observed, this was a very tough hurricane, and he needed to mention it was one of the wettest from the standpoint of water. I don't know if there are hurricanes that are wet because of other reasons. Most hurricanes I know are wet because of water, but anyway, this is actually a good observation for that hurricane. Hurricane Harvey, which hit the state of Texas and specifically the city of Houston in 2017, was unusual because of the amount of water that it dumped on Houston. It wasn't actually a very strong hurricane in terms of wind speed. It was a category 3, and you have a lot of tropical cyclones in your part of the world as well, in the Bay of Bengal. Those events can go up to category 5. This was only a category 3 hurricane, but it dumped an unusual amount of rain. The second, so this is one reason I focus on this specific issue, because the issue in this hurricane, it was rain, and we have much better climate modeling for rainfall than we have for wind speed. So that's why we focus on this event rather than on other hurricanes where the big issue might have been the wind speed, or maybe even the storm surge. So in this case, it wasn't the storm surge, it wasn't the wind speed, it was the amount of rain that was dropped. The second reason probably to focus on Hurricane Harvey, it was a very big event. It was the second costliest hurricane in US history. The first, of course, being Hurricane Katrina that inundated New Orleans in 2005. So this was a very, very big event. There were two other hurricanes in 2017 that were pretty big. There was Hurricane Irma that hit the state of Florida and then went up along the coast further up, the eastern coast. And then there was Hurricane Maria that hit Puerto Rico and damaged quite a lot, caused quite a lot of damage in Puerto Rico, including a lot of mortality. In this case, Hurricane Harvey mercifully didn't kill so many people, but in terms of the damaged economic assets, it was a very big event. Okay, that's why we focus on it. So specifically, what I want to focus on is not just the damage from the hurricane, although of course there's been a lot of work on this. What was the damage from this hurricane? But specifically, I want to focus on the issue of climate change. And why is climate change related here? Of course, hurricane happened because before climate change, actually the word hurricane is a Mayan word that denotes big storms. So, you know, if the Mayans already knew about it, then it's not because of climate change. But the reason I want to focus on this is because this storm specifically dropped a lot of rain because the ocean, actually the Bay of Mexico, where the storm came from, was unusually warm at that point, at that time of year. And because of that, the hurricane had a lot more moisture in it. And because of that, there was a lot more rain that was dropped on Houston. So there is a very clear link. The ocean was warmer because of climate change. Because the ocean was warmer, the storm had more moisture, and because of that, it dumped more rainfall on the city of Houston. Okay, so specifically the question that I want to ask and discuss here is Hurricane Harvey, in terms of the flooding that it caused, how much of it was because of climate change, and what is the implication of that sort of extra flooding that happened because of climate change to the socioeconomic impact of this storm. So can we say anything about the extra flooding that occurred because of climate change? Okay, so this brings us to what we need to talk about, and that's the science of attribution. So this is extreme weather attribution. So this is a literature within the climate science. I'm not a climate scientist. I'm an economist. But of course, I collaborated with climate scientists for this piece of work. And the question is, in terms of the storm itself, Hurricane Harvey, how much of it can we attribute to climate change? Okay, and so how much of it was caused by climate change? And we can say, and we should say, climate change was causing this storm. Okay, in the same way that smoking causes cancer, or the COVID vaccine prevents infection from COVID. So with those two examples, both of these cases, there's not a one-to-one relationship. So you can smoke and never get cancer, and you can actually get cancer without smoking. And of course, regrettably, you can get COVID even if you were vaccinated. But the COVID vaccine decreases a lot your chances of getting infected with the disease, and also, of course, experiencing significant harm from it. So in the same way that smoking is associated with cancer, or COVID vaccine is associated with prevention of COVID, we can say that climate change is associated with hurricanes. And like smoking, or like the COVID vaccine, we can actually quantify that. And that quantification, so by how much climate change has changed either the intensity or the frequency of an extreme weather event, specifically Hurricane Harvey, is what the science of attribution is asking. Okay, so what do I do here? So we take the climate attribution science. We actually take two papers that were done on climate attribution science on Hurricane Harvey. And then we do some hydrological modeling or some flood modeling. And then we link that with socioeconomic data to say something, and you'll see in a minute what I'm going to say, about the climate change impact of Hurricane Harvey. Okay. Now, why am I speaking about that in India? Maybe you don't care about Houston. I'm not necessarily saying you should care about Houston, but basically this method can be replicated for any kind of event anywhere. Okay, so as long as we can do the attribution science, we can do the hydrological modeling, and we have some socioeconomic data, then we can do this kind of analysis, and we can do that for a tropical cyclone that hits the state of Odisha, or we can do that, or for that matter, the Sundarbans, or we can do that for another type of flood events that hits even Uttarakhand. Okay, so there are two ways to think about attribution. Either you can think about the change in the frequency. So Hurricane Harvey became more likely because of climate change. Okay, that's thinking about the frequency. Or you can think about it, this event, Hurricane Harvey, became more intense because of climate change. So in principle, these are two ways to think about the same thing. So these are two sides of the same coin. We can think about it both ways. Either same kind of event, what is the changing frequency with or without climate change, or this kind of event without climate change, what would have been its intensity? It would have been less intense, and therefore we can quantify that. So these are just two ways to think about the same question. Okay. In our case, in the case that I'm showing you, we're going to focus on intensity, but I have another paper that we looked at frequency. This is a paper that was published last year in the journal Climatic Change. But in this case, in the work I'm talking about now, I'm going to talk about intensity. And intensity, we basically have two models, and one of them is saying that about 38% of the rainfall that fell on the city of Houston was because of climate change. So if there was no climate change, so if the last 100 years of carbon dioxide emission or other greenhouse gas emission into the atmosphere wouldn't have happened, then the same storm would have had 38% less rain associated with it. Okay. That's one scenario. That's the scenario from one paper from Reiser and Wiener. And the other one, it's sort of a lower scenario, it's just another paper. They basically just use a slightly different definitions and a somewhat different climate model. They argue that it's a 20%. So 20% of the rain that fell on the city of Houston is associated with climate change. So we are going to do the analysis we're doing with both 38% and 20%. I'm going to present to you the results for the 38%, but it's not really any different for the 20%. It's not dramatically different, let's say. And then what we do is we basically do a hydrological modeling. So we take detailed maps of the city. We know where the flooding occurred in the city. That's the upper left corner. But then we can basically model what would have the flooding been like had there been less rainfall. Okay, so we can provide very detailed flood maps. So say flood map at the actual event, reduce the amount of rainfall by 38%, and you get a different flood map, and that's the C, the bottom left map that you see. So you can see, and the point is that we have very detailed hydrological flooding mapping. So we can actually pinpoint to a specific location and say this house had, say, a meter of rain associated with the flooding that occurred there, but without climate change, the rainfall would have been 38% less, and therefore say the flooding in that location specifically would have been only half a meter, or maybe no flooding at all. Okay, so it depends on the nuances of the hydrological flood modeling. Okay, so this flood modeling was undertaken by Fathom, which is a engineering risk modeling firm based in Bristol in the UK. Okay, so they also collaborated on this project with me. And then what we do is we take the social science data. So we take detailed information about housing, about the houses. So actually they are defined as parcels, but most parcels have one house on them. So this is a piece of land area which typically has one house on it. There are some parcels with more than one house. And then we have data on the buildings themselves, on their structures, and we have damage curves. So damage curves basically tell us what will be the damage if there's a flooding of, say, 20 centimeters, 40 centimeters, 1 meter, and so forth. And then we take the data also from the American Community Survey, on which is basically census tract. So this is not a data at the building level, but at the census tract level. There's still 700 and something census tracts in Houston, so there's still plenty of data. So what we can then do is we look at, for each building in our database, so there's about 1.1 million buildings in Houston. About 105,000 of them flooded during Hurricane Harvey. Okay, but what we can calculate then for those 105,000 buildings, we can know the actual amount of flooding. We can subtract the 38%, so it's not exactly 38% less rainfall. The drop in flooding might be different depending on the modeling. Okay, so we can argue that, for example, this house, 35 Main Street, this house had one meter of flooding, and 50 centimeters would have happened anyway, and 50 centimeters is because of climate change. Okay, we can also translate that to damages and say, okay, this house had $100,000 of damages. $45,000 is because of climate change, and $55,000 would have happened anyway. So for each house in our data set, we can come up with those numbers. Okay, and then we can calculate that for several scenarios. We actually calculated for 7 scenarios. I'm only going to show you the 38%. Okay, we can also say whether the house was flooded. Would have it been flooded without climate change? Okay, so and our definition of flooding is anything with water more than 20 centimeters, because 20 centimeters is typically the average height of the floorboard in a typical house in Houston. So if the flooding is less than 20 centimeters, it's likely that the water didn't reach inside the house. Okay, so that's our definition. And what do we? And this is just an example of where we find the houses that were flooded. So each one of those hexagons describes a certain number of buildings that were flooded because of climate change. But that just gives you a map. That doesn't give you any useful information. What we can do now is link that information with some socioeconomic data. So specifically, we know the value of the home. We know whether it's a multifamily building versus a single family home. We know whether it's located in the official FEMA, the Federal Emergency Management Authority Agency, 100-year floodplain. This is important because if a house is in there, it's insured. It's likely to be insured. Not necessarily, but likely to be insured. And if it's outside of the 100-year floodplain, it's likely not insured. And then we can link that with census tract data about the ethnic composition of the owners of these houses, their median income, and we do some interactions between race and income, which yields quite interesting results. Okay, so what do we find? Well, 105,000, almost 106,000 houses, basically, that were flooded. Now, if you look at, let's stick to the 38% scenario, about half of them would not have flooded without climate change. So climate change is associated with flooding for about, more than 50,000 houses. If there was no climate change, only half of those houses would have been flooded. We can also do the same analysis, and this is the bottom table there, for the damages. And there you can see, again, look at the right column, about $33.7 billion are associated with climate change damages, and only 2.7 billion would have happened anyway. Okay, so why is the difference with about half of the flooded houses being flooded because of climate change, and actually maybe almost 60% of the damages? That's because every house has some, even house that would have been flooded anyway, has some damage associated with climate change, right? Because the flooding became worse because of climate change, and therefore because of that the damage was worse. Okay. What we can then look at, and this is the interesting thing here. So I think, forgive me, but that's why I think this piece of research is interesting. Just quantifying how much climate change damage is an important issue, and in another paper we do that, and we argue that this argument suggests that climate change is being the damages from climate change are being underestimated. But that's a different argument. Here we focus on social inequities, because we can now look at the ethnic composition of the ownership. Okay, so that's basically three types of houses. Type A houses, which are by far the most, so about 900,000 houses, a bit more, didn't flood and wouldn't have flooded with climate change, without climate change. These are the A houses. The C houses are houses that would have been flooded anyway, but climate change made the flooding worse. And the B houses are houses that without climate change they wouldn't have flooded, but with climate change they did. Okay, so if you look at the 38% scenario, roughly half of B and C are roughly the same size groups, right? So roughly 55,000, 55,000 houses are in the B group, and 55,000 houses are in the C group. Okay. Now, what we do see here actually is, and that's the interesting part, is that the Hispanics are much more likely to be represented in those B and C groups, and especially in the C group, but not only, than in the A group. So if you were Hispanic owner of a home, you were more likely to get flooded, and more likely to get flooded because of climate change than other ethnic groups. And specifically, the other ethnic group we look at, that's the information we have, is white, black, and other. So the sort of the bias here is not in this case against blacks, but against Hispanics. Okay, Hispanics are more likely to get flooded. Okay, because of climate change, or even without climate change. But maybe more interestingly, I think, actually, one more thing I want to say here. We also interact actually, I have a slide on that, so let's wait with that. But another thing we can do is the same A, B, and C houses, we can separate those that are outside the flood zone and those that are inside the official flood zone. So just to note, about 75% of the houses that got flooded in Hurricane Harvey are outside the flood zone. Okay. So the reasons for that is, well, two reasons. One is this was a very unusual flood, so might have been more than 100, more rare than 100-year flood, and the flood zone defines a 100-year flood. But I think more the discrepancy here is more because the flood mapping is pretty bad in the US. This is a well-known problem. This is not unique to the US. The flood mapping that's done in New Zealand is, I don't think it's much better. But the flood maps that are done in the US in most places only consider fluvial flooding and not pluvial flooding. So not surface flooding that happens because the surfaces change. And specifically in the city of Houston, we know that a lot of the surface was paved over, and none of this is accounted for in the flood mapping. So what do we see here? And this is again the distinction between the flood zone and the outside flood zone is not because I want to say FEMA doesn't know what they're doing. It's true, but that's not the reason I want to focus here. It's the issue of insurance. The law in the US is that if your house is in the flood zone and you have a loan from the government financing your house, or a mortgage, which finances your house and is owned by one of the federal entities, Fannie Mae and Freddie Mac, which basically almost all homes have, then you're obligated to have, if you are in the flood zone, you are obligated to have a flood insurance. If you're outside the flood zone, you're not. Okay, so that means that if you're in the flood zone, you're much more likely to be insured than you're outside the flood zone. Okay, there's a dramatic difference between the two groups. Okay, and what we see here is interesting, and this is the percent of Latinx-owned properties. You can see that all the bias that we have already identified is in the outside the flood zone group. It's not in the inside the flood zone group, it's in the outside the flood zone group. That's where you see the numbers increase a lot for the Hispanics or Latinx. Latinx and Hispanic are sort of basically synonyms. You see that the bias is outside the flood zone. So not only are Hispanics more likely to be flooded, it's the uninsured Hispanics that are more likely to be flooded. Okay. We can also do a regression analysis. We have plenty of observations. So, we have 1.1 million observations, so we can easily run regressions. And we can show, for example, for example, the proportion Latinx is clearly associated both with the depth of the flood and with the damage, sort of the climate change part of the depth of the flood and the climate change damages. Okay, so if you are a Latinx owner, then you're more likely your depth of flooding because of climate change will be higher, and the damages will be higher. Okay, you don't observe the same kind of biases for Black or for the other racial groups in Houston. What you do observe, and this is maybe worrying, is that generally speaking, higher income is associated with more flooding. Okay, that's not unusual in the US. So a lot of times, because the richer communities are next to bodies of water, because that's the nicer parts of town, on the coast or next to the river. So you a lot of times observe higher likelihood of flooding associated with higher income. But in this case, when you interact that with the Latinx variable, you observe this negative coefficient, which means that, yes, in general, higher income is associated with more likelihood of climate change-induced flooding. But for the Latinx community, the relationship reverses, and it's actually the lower income Latinx population that is more likely to get flooded. Okay, that's a different way to show that. So if you look at a sort of a 25,000 income, average income in a tract, and a 75,000 and a 125,000, and you see that the highest likelihood of flooding is for those Latinx low-income population. They are the ones who are most likely to experience this climate change impact. Okay, so what are the sort of the key findings from this piece of research that I wanted to talk to you about today? Neighborhoods with more Latinx residents have more climate change attributed flooding. Neighborhoods with higher income had more climate change attributed flooding, but it's the low income Latinx neighborhoods that had more climate change attributed flooding. And lastly, it's the low income uninsured Latinx neighborhoods that had disproportionately more climate change attributed flooding. Okay. So why do we care about this? Well, I think there are various reasons why one should care about this. One example is, I think, that's one way to convince people that climate change is real. And we actually think, and we might even do it, try to send letters to all these houses that were flooded because of climate change. So remember, out of the 110,000 houses that were flooded, 105,000, half of them were flooded because of climate change. We can actually identify those houses and send them a letter, say, you know, dear Mrs. and Mrs. Smith, your house was flooded because of climate change. What do you think about that? What's your, you know, are you reducing your carbon footprint and so on and so forth? So there's a lot of sort of research questions that one can ask, but the point is this a convincing way to convince people who are reluctant to do something about climate change to actually make it personal? Your house was flooded because of climate change. There's a lot of other reasons why this. For example, that might be a liability issue. So potentially, a specific homeowner that knows that their house was flooded because of climate change can then sue the city for not doing enough about climate change, or can sue the oil industry in Texas for not doing enough about climate change, or if we apply this same logic to countries can sue other countries about the damages from climate change, because we can now identify very specifically the amount and of damage, and specifically who bore that damage. Okay, so in this case, in the city of Houston, we can actually say it's Mr. Smith, or it's, you know, Mrs. Whatever her name is. Okay. So these are some reasons, I think, why that kind of link between climate change and the economic costs of extreme weather events can be done through this attribution work, and could potentially be a game changer in terms of liability, in terms of compensation, in terms of sort of legal consequences, and in terms of actually perceptions of people about climate change. I'm happy to answer any questions if there are any.
Thank you, Professor Noy, for a wonderful presentation on a topic, and which is really very time relevant as to you know, we have to realize whether the impacts of climate change are more severe and how we can quantify those impacts. Thank you once again. May I now request your questions?
There is one question in chat box by Professor Bharadwaj.
Can I see it? Yes.
So Alok, if you want to say, like, speak out, I think you can unmute yourself. Subir, would you like to read the chat box?
I cannot see.
I'm not able to see it because I think it has been addressed to you.
Okay. So I can read quickly. So Professor Bharadwaj just mentioned about do buildings damaged from inside are considered as part of the damage after a flooding event? Second part of this question is how to account for such damage that may not be visible in high resolution satellite imageries.
Yeah, so the damage estimates are not from satellite imagery. They are from damage functions. Damage functions that were constructed by the US government for, I think, several, originally from the US government, but then modified by the engineering consulting firm that we worked with. And these are available for, I think, 35 types of buildings or something like that. So they try to account for the value of property inside, but of course we don't know what's inside a specific house. These are just, these are valuable as average damages rather than a specific damage for a specific house. So those damage functions basically tell us, this type of house, say a wooden frame house with this type of roof, would get that kind of damage from, say, 20% of the value of the house with a half a meter of flooding, and 70% of the value of the house with a meter of flooding, and 100% of the value of the house with, say, 2 meters of flooding. Okay, so these are not based on satellite imagery, but on these damage functions that were constructed based on past events and the quantification, sort of on the ground quantification of those damages. Okay, and this potentially is a problem if the housing stock is very different than the ones on which these damage functions were constructed. In the case of Houston, given its location, we don't think that's the case. So I live in a city which is on very steep slopes. The kind of damage functions you would get when you do, when you develop flooding when you observe on flooding on the ground would be very different than the damages you would associate with very steep slopes. So their damage functions wouldn't be appropriate, of course. In my case, in the city of Wellington in New Zealand. But in the city of Houston, we think that the damage functions are pretty good as averages. They're not specifically telling, Mr. Smith, your damage to your house was X, but damage to the kind of house that you have is X. I hope that answered the question.
Thank you. I'll quickly read another question from one of our PhD student, Ms. Richa. My question to you is that where does the environmentally induced migration fit into the continuum of climate change adaptation options?
So migration in what? Can you repeat?
Where does the environmentally induced migration fit to the continuum of climate change adaptation options?
Well, migration is clearly happening. Although remarkably, we haven't been able to sort of quantify it very well up to now. In this case, I don't think it's relevant, right? So just to point out, in the city of Houston, we haven't seen any evidence of much migration because of Hurricane Harvey, unlike Hurricane Katrina that flooded New Orleans in 2005 and was the costliest hurricane, which induced massive migration out of New Orleans. And New Orleans still today, which is 16 years later, is still significantly smaller than it was the day before the hurricane. Smaller in terms of population, because there was a massive induced migration. More broadly, so this is because of an extreme weather event. Can we quantify? We know that extreme weather events cause migration. We know that happened in New Orleans. Of course, it happens a lot more in maybe low-income countries where there's fewer adaptation options and fewer resources for reconstruction. We don't really know. We know that they are because of extreme weather events, but of course, extreme weather events are only partially associated with climate change. That's exactly the point that attribution science is trying to make. So exactly how much of that migration that is happening because of extreme weather events is associated with climate change, we don't really know. Okay, we don't have the tools yet, I think, to quantify that. But migration is definitely an adaptation strategy that is being adopted. I actually have a paper published on this issue of migration last year, again in the journal Climatic Change, that tried to make a sort of another point about migration and how the interaction between the need to migrate because of the climate change impacts and actually the desire to, or potentially the possibility extracting compensation for climate change damages. So, this is basically a framework we call exit and voice, based on the framework developed by Albert Hirschman back in the 1970s. And we investigate that within the context of countries that are exposed to climate change impacts. But that's sort of a different topic than this attribution science, because we haven't really been able to adopt this attribution science to migration, although that might be a next step, right? But then we will need more data. We don't have the kind of data that would enable us to do that at this point in time, I think.
Subir?
Yeah, can I ask a question very quickly? Yeah, so I was wondering that this work was partly possible because you had very well-defined maps at your disposal.
Yes.
I believe these are long time series maps so that you can compare and overlap and see the changes over time. Now, suppose if you have to do a similar kind of exercise in the Himalayan context, where maps are very difficult, first of all, their availability is really a very tricky issue, and secondly, the resolution also may be very varying in nature. So how can you see such kind of maps, and the amalgamation of science and social science can help inform policy making, especially in the developing economies context, with a special reference to such terrain like the Himalayan region?
Yeah. I think that the main barrier is not necessarily the maps. It's actually the attribution part. So attribution science, so this how do they do attribution science? They run they develop a model that specifically replicates a specific type of extreme event. So say you have a big, I forget the name of the tropical cyclone that hit the Sundarbans earlier last year. Was a cyclone.
Not Ayla. What was that?
Ayla was a few years ago.
Ayla was
like 10 years ago, right? Let's say
Yeah.
cyclone Ayla, because I don't remember the more recent one. The one that hit Kolkata. Yeah, anyway, so Ayla.
Are you referring to Funny?
That could be. Anyway, doesn't really matter. The point is an example. So what we need is a climate model that describes this specific event, say her tropical cyclone Ayla, and then tries to and rerun the model without the greenhouse gases, and see what is the likelihood or intensity of that event would have been without the greenhouse gases in the atmosphere. Okay, so we need a lot of climate science to develop those. Just this number, the 38% that I used in this work, which we collaborated with the people who came up with that number. That number there's a lot of climate science behind it. So if you look at the climate attribution research, nowadays there's about 100 extreme weather events that are being analyzed every year. Maybe a bit less than that, globally. Okay, and so this is a major effort. So just to give you an example, the people who were looking at those attribution scientists were looking at the event, the heat wave event in North America that happened earlier. When was it? I think it was in June. Or July, and they ran the model and basically said this heat event wouldn't have been possible without climate change at all. Okay, and just to do that event, there was about a collaboration of 30 scientists that worked full time on it for about 3-4 weeks to develop that conclusion. Okay, so this is a major effort for just one event. The thing is, between let's say the 100 events that are being analyzed every year, almost all of them are in high-income countries. So there's a lot of attribution science research on events in Europe, for example, on the floods in Germany just a few months ago, or in North America, or for that matter in New Zealand and Australia. But there's very little attribution science being done for, say, events in India. Okay? So we don't have that attribution science part. Once we have the attribution science part, I think that the maps could be, we don't need time, we didn't use time series maps. We just needed one good detailed map. So I think that those are becoming much more available. And you could combine that with remote sensing data, which is now available at a very high resolution. So the Sentinel product or the MODIS product, which is available, the Sentinel product is available for free for the whole world, which is available, I think, free at 50-meter grid cell, but there's potentially other products that are even much more detailed. And once you use those, and I think India also has a network of satellite remote sensing data that can be used. I forget the name of the, but there is. I know there is because my collaborators on the Sundarban project at the ISI in Kolkata looked into that. So that you could use remote sensing satellite pictures instead of maps, and then develop some AI algorithm to translate those into sort of usable information, which you can then combine with the attribution science. But the main barrier would be you need the attribution science. So you need, for this specific hurricane that is hitting the, say, the coast of Odisha, you need to actually be able to say something about the probabilities change or the intensity change, and then you need to develop the flood modeling. Okay, those seems to me to be the barriers rather than the mapping. And socioeconomic data, India actually has quite a lot of that, right? So the district level and so on, you have quite a lot, or even below the district level. In the census, there's quite a lot of information. Yeah.
Thank you, Professor Naik. Thank you.
So, if you allow, I think there is maybe a last question. We have it in chat box.
Please go ahead.
So it's from another one of our PhD student from Earth Science and Center for Disaster Mitigation. He is asking, is rehabilitation is a good mitigation strategy for people living in floodplain area? If yes, then what are the challenges in terms of livelihood, jobs, etc.?
I think that deserves a different talk, I'm afraid. So, this is a very big question and has to do with, one of the main tools we have to deal with climate change adaptation is managed retreats. So to do a managed retreat from specific locations, because those locations are more dangerous because of climate change. So, for example, if you decide, if your society decides that living in a 1 in 100 year floodplain is fine, because that it still means that on average this event happens only 1 in 100 years. But if the intensity, the frequency changes and now it becomes 1 in 10 years, then that's no longer a viable place to be, and you need to retreat from there. So you need to move people from there. How to do that, and how to do that fairly and equitably and efficiently, is a big challenge. It's a big challenge in New Zealand. So I'm actually involved with the government now on designing a managed retreat act, which will help us sort of get the mechanism in place to do that kind of managed retreat. It's a problem in India because some places are clearly going to become untenable and we will need to move from them. It's a challenge in the US, it's a challenge in Japan, it's a challenge everywhere. And every country, it might be the specifics might be different, but it is roughly the same challenge. The specifics in terms of where are the big risks? Is it in river deltas? Is it on the coast? Is it in floodplains inland? And so on. That depends on the specific issues around each country. In your case, I think in the foothills of the Himalayas, it's more difficult because modeling the flooding is much more difficult on mountainous areas than it is in the sort of the lowlands. So in this case, understanding where the risk is shifting, which necessitates moving people, is much more difficult. Yeah. But I think I end there. I have a bunch of papers that look at managed retreat in the New Zealand context, not in the Indian context. But there's a lot of work that needs to be done on that globally.
Thank you, Professor Noy. And now it's to the Professor Subir. I'd like to close this session.
Yeah, I thank Professor Noy for this lecture and accepting our invitation to be part of today's proceeding. And it would have been really nice to have you here in person, but as you know, we are still unsure about the pandemic. But I hope that once we go back to business as usual normal situation, we will have you in campus, and then we can have much more fruitful discussion on topics which you specialize. And I hope all the participants have gained a lot from your lecture, and because of paucity of time, they were not in a position to ask questions, but they will get in touch with you in due course. Once again, I thank you on behalf of the center, on behalf of the institute, for accepting our invitation, and we hope to see you soon again. Thank you, Professor Noy.
Thank you very much. Thank you, Sumit. Thank you, Subir, and thank the audience.
Thank you, Professor Noy. I may request you to unshare your screen, please.
Yes.
Thank you. And you're more than welcome to stay back for the next lecture. But I know it has been late for you. It is almost 8.
Yes.
Yeah. So please, thank you.
Thank
you
very
now
much.
Now may I request Professor Arya to introduce our next speaker, Professor Goswami, please.
Professor Sumit Sen, thank you very much. Good morning, everyone. And before I speak anything, I would like to congratulate all of you on International Day for Disaster Risk Reduction. So on my personal behalf, I welcome all you all here in this program where we have 3 special sessions, and we have very renowned speakers here. And in this series of lectures, the second lecture is given by Dr. Bhupendra Nath Goswami. He is such a renowned person, I feel like, introducing him is something like showing a diya to Suraj. So this is the kind of thing that I feel. So, sir, very good morning.
Sir, you are muted.
Good afternoon.
Yeah, good afternoon, sir.
Yes.
Yeah, so friend, Sumit has given this nice opportunity for me to, speak more about yourself. And it also gives me a chance to look at, so many things that I wasn't even knowing about you. So, sir, I would like to introduce you. Sir is a very renowned meteorologist, climatologist, and as you all know, he was the former director of Indian Institute of Tropical Meteorology. It is located in Pune. And currently, he is the chair professor in one of the ISER that we are having. His work on monsoon dynamics is very well known to everyone. Whosoever is working in the area of climate change. And see, the climate change we all know now, but he is working since 1975 or 78. And it was the time when he was a postdoctoral fellow in MIT. Amazing, sir. I'm really happy to meet you.
Thank
even
you.
if it is online. And I'm so happy to introduce. I really would not like to read, so many papers, so many books, so many reports of you, but there are few things that are very remarkable.
I think you should make it short. It is not necessary that you mention.
Sir, you are elected member of 3 Academy of Sciences in India. It's such a rare credential that anyone is having here. You are fellow member of Indian National Science Academy, Indian Academy of Sciences, and National Academy of Sciences, and you are also a member of World Academy of Sciences. I'm very happy to introduce you, sir, to my colleagues, to my students here. And sir, I welcome you here. And also, sir, you are the recipient of Shanti Swarup Bhatnagar Award, which is the apex award given by CSIR to anyone. So, sir, I welcome you all here. As you said, I'll keep it short, and we would like to listen more from you. So, sir, welcome to this session. And now this platform is over to you, and kindly enlighten to us as well as to our student more about the monsoon, climate change, and how we can apply it in the area of disaster as well as in the risk reduction. Over to you, sir.
Thank you so much. Thank you so much for the introduction. Subir, how shall we? Can I share my?
Yes, sir. You can share your screen.
Okay. Are you able to see my screen?
Yes.
Okay. All right. Okay. Thank you so much for inviting me for this occasion. It's a pleasure to be here. I will be talking about the climate emergency and how it sort of affects monsoon. Largely, the talk is more of a sort of for the students rather than the researchers, because I'm going to concentrate mostly on the big picture rather than the nitty-gritty. So,
Professor Goswami,
yeah,
I'm sorry. Can you make it full screen, please?
Yeah. I'm going to make it full screen. Okay, here you go. It's okay. Okay. All right. So there is no doubt that today the climate, the Earth's climate, has reached an emergency point where the Earth is constantly crying out, because the the Earth's climate change has taken place mainly because of the degradation of the environment, and the degradation of the environment has been caused largely by, I'll show that, largely by the human population growth. And as a result of today, the exploitation of the environment is so large and so deep that Earth is unable to sustain the whole the population at present, and that is why many of our problems have come up. And this has been alluded to by many even artists and authors of in various places. So what if the interesting point is that the Earth has the beautiful climate that we live in today is very unique in the whole universe, and it has evolved over the last 4.6 billion years. And it has evolved to something which we call Goldilocks climate, which is not too hot or too cold, and which can sustain and thrive, where life can thrive. This climate also has a temperature which is close to the triple point of water, where all the 3 different phases of water can coexist, and this makes a very large impact in the heating distribution over the globe, and that affects our climate variability and also makes it a perfect condition for human habitation. However, the humans have evolved only over the last 12,000 years. But within this short period of time, we have changed the environment so much that today the degradation has come to a point of almost no return. And what we now know is something like a 6th mass extinction is on the process. So this is where the seriousness of the situation is. So as you know, the population of the Earth has grown slowly in the beginning, but over the last 200 years, it has exploded from 2 billion to about 8.6 billion today. And this increase, explosion of population is very much related to also how the carbon dioxide in the atmosphere has grown. And that is essentially related to the human activity. As we started by about 10,000 years ago, the Earth's carrying capacity or sustaining vertebrate population is about 200 million tons, and that is what happened about 10,000 years ago. But as the population grew, we needed more resources to sustain. So we started exploiting the resources, like as we started agriculture started cutting down forests and hunting more animals, and as a result, we are more exploiting this the environment more than that it can generate, and as a result, we are over exploiting it. And today, I'm sorry, today we I think over exploit it more than 5 times that it can generate, and when it happens like that, the carrying capacity itself gets degraded, and at some point of time, it cannot sustain the population at all, and therefore the population itself must decrease. And that seems to be happening today. And already what I call the 6th mass extinction, it has initiated, because I think the Earth has gone beyond the point of carrying capacity, and there is a feedback which is making the population itself to decrease, and that is, I think, the situation. And this is why I think that, and this is all related to the climate change. And of course, what is climate change? I don't want to go into great details of describing what are the effects of the climate change today, but what I'm going to do is just to mention that the manifestations of climate change are now not very visible in many different areas. For example, sea ice extent is seriously decreasing. In the summertime, the sea ice extent is it has been over the last several decades has decreased by about 50 to 70%. And similarly, the Greenland ice is decreasing significantly. The forest fires, the Siberian fires are increasing tremendously. This is causing the peatland fires are burning the burning in this and adding more carbon dioxide in the atmosphere. Also, it is producing methane. The warming is causing this peatlands are now producing more methane and carbon dioxide, which is further adding to the greenhouse gas. So, this is a kind of a feedback that we must be very concerned. In fact, last year, the heat wave that hit the Siberia was so huge that the temperatures in Siberia are just like, like in places like India, 38 degrees several days. And as a result of that, and it continued for more than a month, and this kind of a heat wave can actually change the dryness, cause a lot of fires, peatland fires, and those, again, as I said, cause the more carbon dioxide into the atmosphere. So these are, as the previous speaker mentioned, that these are like, these are once in several 100 years event, and more than that, and therefore these are like entirely due to climate change. So these events have started becoming much more frequent, and that is the cause of concern. So it has definitely come to a emergency situation, and this has been recognized. As a result of that, of course, in India, one of the major effect that we are beginning to feel very clearly is that the flooding, the intensity and frequency of the flooding events over almost every year, they are increasing in numbers and intensity. Except this year was a slightly, I think, different, but more last several years we have been seeing more and more flooding events, and this has been highlighted by the IPCC sixth assessment report, where it has now the sixth assessment report has very clearly sort of makes that sort of highlighted that the time is running out. The way we are going in terms of the greenhouse gas emissions and not able to cut down to the level that we want, there is no doubt that the increase in the temperature by the end of the century will be more than 2 degrees. And when the temperature increase at the end of the century century or higher earlier is more than 2 degrees, we are going to have a very serious situation where we may not be able to come back at all. And this is the critical. I'll come back to and I'll explain why that is so. And this is what is the emergency situation. So because I'll explain why that is so. And this is a very, very important point. And that I think this time the sixth assessment report made it very clear. The earlier reports were a little bit more conservative about it, but the amount of evidence that is available today is so clear that the sixth assessment report was very vocal about it. So what I'm going to do is to try to quantify what is the climate change and sort of give it science behind it. The climate change in some, the science of climate change is simple at some level, but it is very complicated at another level. And why it is emergency situation now. And finally, actually, I'll concentrate on what is in store for Indian monsoon. What is going to happen to the monsoon rainfall in general? What is going to happen to our extreme events, both heat and rain extreme events, and that is the most important part. At the end, I will try to talk about some adaptation issues, especially focusing on Northeast India, because right now I'm not. I'm more focusing on Northeast India, where there is very little work going on, and there are two issues that I'd like to touch upon. One is the flood forecasting over the Brahmaputra basin, and the other is sort of impact on biodiversity. So basically, we should be able to give good warning about the hydrological disasters which are going increasing in the Northeast as well, and what kind of adaptation policy we could adopt. So climate change, of course, the indication of the climate change is, or global warming is, of course, the increase in the global mean temperature, which has now been established quite well. And we know that today it has increased about 1.09 degrees with respect to the pre-industrial level. So these are anomalies of the global mean temperature with respect to the pre-industrial reference level. And that is based on several instrumental data and some proxy data, but mostly during this period, mostly instrumental, different types of instrumental data, and by correcting all kinds of biases and things like that, that is uncertainties that is there in the data. So with all that, now we are confident that this increase is real. So this is, of course, due to the increase in the greenhouse gases. There is a lot of modeling studies and indicate that this is clearly due to the increase in the greenhouse gases. Of course, carbon dioxide is the main. The other is also methane, which is increasing. For example, carbon dioxide, the current global mean carbon dioxide is about 414 parts per million, while that is that of methane is about 1888 parts per billion. I'm just giving these two numbers just to just to give you a sense of how much we have, how much it is increasing and how it refers to the past. In the past 1 million years. So if I put that into context of how carbon dioxide and methane changed over the last about 1 million years, for which we have data now from the Antarctic ice core. From this Antarctic ice core, you can find out the ice core contains certain air bubbles, and there you can measure the carbon dioxide and methane from those ice bubbles using mass spectrometer and gas chromatograph, etc., etc. So that is now pretty well established, and that indicates that, and from delta oxygen, the isotopic ratios of deuterium, you can also get idea about the temperature variations. So these temperature variations indicate those glacial and interglacial periods. Like this is a glacial period, this is an interglacial period, and we are now at an interglacial period. The glacial periods are normally longer, but the interglacial periods are shorter. And but the change from glacial to interglacial are much faster. So these are certain characteristics which are now we know very well. Associated with these large glacial and interglacial cycles, the carbon dioxide and methane also changed. And how it changes, of course, there are certain dynamics associated with it. But point to note is that the level of carbon dioxide, even in the earlier interglacial periods, were never greater than 220 parts per million, 280 parts per million. Whereas today, of course, in the glacial periods, it goes down to about 200 parts per million. It goes up to about 280 parts per million at the interglacial period. But today we are at 414. So this is almost 40% larger than anything that happened in the last 1 million years. Okay. So similarly, the methane was never more than about 600 parts per billion. So it's about 600 parts per billion or 700 parts per billion was the largest amount measurement in the 1 million years. But today we have 1880 parts per 1900 parts per billion, almost 3 times larger. So these concentration in the of both carbon dioxide and methane in the atmosphere today is unprecedented in at least 1 million years. Even before that, up to about 3 million years, we think we have not seen anything like that. So therefore, this is a very serious situation, and we should be concerned. And this in the now this is the point that I mentioned in the beginning, that if the temperature increases beyond a certain point, we may not have a possibility of turning back. That comes from the fact that if you look at the history of the temperature, global mean temperature over the last 500 million years, and let us concentrate on the last 60 million years. There is considerable paleoclimatic reconstruction of various data, and somebody has put together all that into this graph where we have the temperature is seen. You might notice that these scales are very different. It has been expanded in all about in a different way, highlight the recent to highlight the recent period. So what is not interesting to note is that over the last 60 million years, Earth has been generally cooling. That is normally happening because the Earth was cooling from the beginning, right from the beginning of the evolution, but slowly they were cooling and coming to the present temperatures. And by about 3 million years ago, it reached the level of about roughly about 14 degrees global mean temperature, or between 14 and 15 degrees global mean temperature. And that time, these oscillations started in the climate, and climate remained more or less stable over these period, last 3 million years. These oscillations, now known as Milankovitch cycles, these are the glacial and interglacial oscillations. In the last 1 million years, they are about 100,000 years period. Before that, they were about 42,000 years period, but they were oscillating. but they were remaining more or less for about have been somewhat stable equilibrium around stable oscillatory equilibrium. This stable oscillatory equilibrium is due to the forcing of the sun's radiation, which varies with the orbital parameters. And these produces certain feedbacks which can take it to a colder period, and then some other feedbacks can bring it back to warmer period, and this remains. This happens to maintain this oscillatory equilibrium. Now that seems to be can happen only if the Earth cools to this temperature. It cannot happen because the perturbation in the solar energy is so small that it cannot happen if the mean temperature itself is very large, and that is seems to be what happened. We did not have these oscillations before 3 million years ago, and at that point the temperature was like what would be about the mean temperature about about 14.5 or 15 degrees. Now, if that increases to 2 degrees, then we'll go to this level, and this level, then I think that will be impossible to come back. There may be other effects. Other effects will take over, and maybe we'll have a runaway greenhouse effect, and the temperature will go in the opposite direction. And that is what we are worried. Okay, coming back to who is responsible for this. Of course, we need to fix responsibility, but to understand how to control this, we have to first know where it is coming from. And as far as the carbon dioxide is concerned, now the data is quite clear, and we know that some of the industrial countries like USA, they started putting on carbon dioxide way back from the beginning of the century, 20th century, and of course they accelerated in the recent times. Then this is mostly I'm sorry, this is the top one is
it is China, sir.
China. I'm sorry, I'm unable to see that. China, the next, China has started late, like India, but look at, but today they are contributing a whole lot, and that is something important. For example, the United States, on the other hand, they started all the way from the beginning of the 20th century, and then they started. So their cumulative contribution is much larger. Similarly, the European Union, then India is also started very late, and then today we contribute about 7%. Our cumulative contribution has come to about 3% altogether. So this is the kind of total, about 36 gigatons of carbon dioxide is there in the atmosphere today, and that how different countries have contributed is shown in this sort of somebody prepared this interesting figure. So we have to consider these contributions by different countries. But some of the Russia has contributed significantly to some extent, but these are all other countries. So in terms of fairness, as far as per capita, India contributes small 2 tons per capita, but like United States contributes almost 17 tons per capita. Even Saudi Arabia contributes for the number of people they consume a lot, and so. But we cannot simply go for per capita. This is something we have to use, that we need more energy, but at the same time today, even whatever we have to we are contributing, we have to be responsible for it, and we have to reduce ourselves. Even if we are per capita, we are doing less. So, so as I said, India contributes 3% to the cumulative, whereas China contributes about 7%. China contributes about 13% today. So this is something that for policy making, these numbers need to be sort of taken into account, and the people who have contributed more must put more effort, not only today, to reduce them. So as far as in terms of science of climate change, the basic science is very simple. So it is basically energy balance. So the sun's radiation tries to warm up atmosphere. It comes to the atmosphere, and then most of its energy actually goes to the atmosphere, because atmosphere is more or less transparent to the visible radiation. The sun's energy is maximum in the visible radiation. That window is kind of transparent almost. Therefore, most of it goes to the surface. Surface gets heated up. The earth gets heated up. Then earth as a black body radiates. The radiated energy then tries to go out. And then because the atmosphere has these greenhouse gases, because of the temperature of the earth, now it radiates not in the visible range, but in the long wave range, infrared range. That infrared radiation has a lot of absorption bands in the atmosphere, and therefore a large amount of the emitted radiation gets absorbed in the atmosphere, and that gets re-radiated back, and therefore the temperature, as a result of that, ultimately the total amount of energy lost to space as a result of reflection as well as long wave radiation leaving the atmosphere, plus has to balance with how much radiation is received by the earth, and that can be balanced in a very simple equation, where suppose this is the solar energy per unit area, and this is the reflectivity, Earth's reflectivity. It's called albedo. So certain amount of energy is reflected by clouds, ocean, vegetation, everything, ice, and average is about 30%. 30% of the incoming solar radiation goes out. So 1 minus alpha into S zero, and this is the disk of the Earth's disk, which receives that much radiation all the time. So so on the other hand, when the Earth radiates, it radiates all over the globe. So you have to multiply it by all area, total area, and it is governed by Stephen-Boltzmann law, T to the power 4. And this is a factor which is called infrared transmissivity. So how much fraction of emitted radiation is transmitted to the space? So suppose at present, I think it is about 67% or so. So this is an important factor. So once these two balances, we get an equilibrium temperature. So there are three important factors: how much solar energy is coming, how much is reflected back, and what is the absorptivity of the atmosphere. These three factors basically control our temperature in a very simple way. And if I have those numbers, I can actually find out what is the mean temperature. Suppose I did not have the transmission, the greenhouse gases in the atmosphere, and everything was lost, then my temperature will be like 255 degrees, minus 18 degrees Celsius. In other words, the greenhouse gases in the atmosphere actually makes it warmer. And that is because a greenhouse gases allows less amount of radiation to escape. If less amount of radiation is escaped, it has to balance with more solar radiation. So to increase the amount, you have to increase the temperature so that it radiates more, and then the amount that is retained become lost to the space becomes equal to amount received. So the necessarily there is a greenhouse gas effect, and that is what makes the Earth's temperature very unique. Now that natural greenhouse gas, then if it is perturbed, now today we are perturbing that greenhouse gas, and that is because we are introducing this 40% or 50% increase in the greenhouse gas concentration. That increases the temperature. So that temperature increase is the anthropogenic effect. So that is what we try to estimate. Suppose we double the carbon dioxide, what will be the increase in the temperature? That is the sensitivity that we need to know. So But it is these three factors are very important in giving sort of understanding the temperature in all planets, for example. So depending on where you are, the amount of solar radiation received is different. So suppose away from closer to the Earth, you will get more solar radiation. And further away, you will get less solar radiation. But depending on what is your albedo, so albedo of Venus is very high. It has a carbon dioxide atmosphere, and as a result, even though the solar radiation at the top of the atmosphere is high, but what it receives at the surface is small. But it does not let that energy go out because only 12%, 22% of that energy only goes out. As a result, it builds up, and that temperature at the surface becomes high, very high. On the other hand, of course, in the body Mars, not only it receives less energy, but its reflectivity is also very low. Therefore, the temperature is mean temperature is very low. So all these it is relatively easy to understand from the basic principle. But the complexity comes from the heating distribution in the atmosphere is affected by a lot of internal processes, and internal processes are one of the important part of the internal processes is the clouds, and the clouds have and the entire spread of different large it comes in a multiple scales, and all these scales affect our large scale heating here. So the clouds release latent heat, and the ITCZ, for example, has a very large scale ITCZ. The heating over this whole region caused by the clouds affects the climate, but that comes from all these processes like water drops, which are formed from CCNs, which are very small micron scale, which form into cumulus clouds of about a kilometer scale, which then form into cyclone scale synoptic disturbances. They then get embedded into these ITCZ, which produces a large scale. So to get the large scale heating, I have to have information on all these different scales, and that is very difficult to do in a modeling setup because you cannot resolve all these cases. This is like a turbulence problem. So this is where the whole range of clouds actually, this is an example. There are many different examples. This is the complexity in the atmosphere and the climate. And this is for this only, this times the complexity actually is recognized by the physical community. And to this year's the Nobel Prize went to climate scientists because of this complexity. And so this is what makes it difficult to make a very single deterministic estimate. But also there is other feedbacks in the system which are very important, and that feedbacks also produce a lot of complexity. One of the probably the feedback is that the high clouds, for example, depending on the cloud, let us remember that water vapor is also a greenhouse effect, a greenhouse gas. Now, the clouds, depending on their types, it can be either more reflective. For example, high clouds are less reflective, so it penetrates, the energy penetrates, but it also more long wave radiation, which is allows less of long wave radiation. So it produces returns back more long wave radiation. So then the low clouds, on the other hand, more reflective, so the albedo is more, so the greenhouse effect is less. So here the high clouds have a more greenhouse effect, the low clouds have more albedo effect. Now the clouds can produce the two things, and so suppose let us think about the carbon dioxide increases the temperature, the global mean temperature. The global mean temperature produces more evaporation, more moisture in the atmosphere. More moisture produces more clouds, but suppose it produces low level cloud, it will reflect more radiation. Therefore, it will produce global warming. It will add to the global it will cool the sort of reduce the global warming. Suppose there is more low level clouds, it will reduce the global. On the other hand, suppose there are more high level cloud, this high level cloud have more greenhouse effect that will further add to global warming. So we have two different contrasting. Now the question is, we have to be able to get the right amount of high level cloud and or right amount of low level, and that is a challenge. It is also, there is this, we should be concerned because, as I mentioned in there are certain tipping points in the climate. So as if you go beyond a certain equilibrium value, then it may not be able to come back. It will go to a different climate altogether. And this is illustrated by the same point that I mentioned in the beginning, is that suppose I take temperature and sea level as the two parameters in the space in the space of temperature and sea level. If I put together the last 100 million years, the glacial interglacial period, they will show that the interglacial period has high sea level, but glacial periods have low sea level. They keep going in circle, and this is an equilibrium. But today's temperature is somewhere here, and which is already gone beyond the last, the largest, the interglacial temperature. So we are already beyond that. But if I go a little bit further, but if I do now a lot of control measures like the emission cutting and various other measures, maybe there is still possibility that we may be able to come back to this level. But suppose we do not do that, what will happen is that it will go to a 2 degrees level. And then once it goes to 2 degrees level, then it will be impossible to come out. Then it will go to other warm climates as we have experienced in the past. There are several examples of that in the past. So it is possible that if it is if it warms up more than 2 degrees, then we may have to go to a very large, much warmer period where all the other ill effects of the mass extinction will be much faster, and the other things will happen. So this sixth mass extinction is apparently on the way, and there is a lot of evidence that the rate at which the vertebrate population is decreasing has been much more than 10 to 100 times larger than in the previous century. And this is, there is several papers now that try to quantify this, and that seems to be happening. But why this? But this is not a unique mass extinction. It is a unique mass extinction because in the past also there are about 5 mass extinctions in the past in the history of evolution, but they are all by natural causes. This particular one is related to the growth of the population. The gradient, the way it is increasing, is very much related to in the population explosion in the last 200 years, and that is a cause of concern because the people are because now are societal problems we have to take because the people, earlier mass extinctions are all natural, so there is nothing you could do about it. But today we could do, but it is caused by human. But the humans are rather selfish and they're greedy, and for the unscientific reasons they will continue to do what they are doing, and therefore it is difficult to even predict whether we will be able to stop this. So this is what makes it very, very serious today. And I see there are signatures of this mass extinction is the COVID is another example. I think there is a study that shows that the COVID is actually accelerating this. So of course, there's a very new study, so I'm not sure that how much we can see, but the ecologists and environmentalists are very concerned about that. This kind of a perturbation now will have an important sort of triggering effect of accelerating the mass extinction. So based on all these that we know today, people have made sort of vulnerability estimates, which regions are more vulnerable and to this climate change. And suppose we have a 3-degree increase at the end of this century. India happens to be one of the places where it will be most vulnerable, most affected. Partly the largest exposure comes from the heat wave and water stress. The water will be a big issue coming years. Power reduction, crop will change. These all will in human habitat degradation, like discussed in the previous talk. So these all will affect us more because of our population and this limited space. So that is something that we should keep in mind. So therefore, today we have to do maximum that we can do to stop this, and we are not doing. The Paris Agreement failed, and many countries went back, and therefore I think in the COP26 countries have to agree to do much more. Otherwise, the future population, future generation will have to suffer. So let me now come back to what is there in store for the monsoon. So this is the kind of general background, and on that we have looked at, of course, our main interest. We have done a lot of studies about how monsoon is being affected by these. Two things I will mention here, not everything I cannot mention. Just one of the things is that the one question that was always there is that the global warming, with the global warming, as the temperature is increasing, the moisture content in the atmosphere is increasing. Definitely, it is increasing. Every degree increases 5% increase in the vertically integrated moisture content. Now, as the moisture content increases, you expect that the precipitation should also increase. The potentially precipitation should increase, but whether actually precipitation increases or not depends on regions and the dynamics. Because precipitation does not simply depend on the total amount of moisture, but the moisture has to be cooled and precipitated. The cooling of the precipitation does depend on the dynamics. So it automatically does not say that a monsoon precipitation should increase. And what we find from the records over the last 200 years, we have a good record of monsoon rainfall over the country. It doesn't have a very strong increasing trend. But when you look at carefully, there is an increasing trend, but the trend is rather weak. So we estimated by using nonlinear trend analysis, and by removing all the effect of the oscillatory modes, etc., and we find that the increase in the mean amount of monsoon rainfall. By the way, this curve shows the variation of all India monsoon rainfall as a normalized by its own standard deviation, as a departure from the mean. So these are deviations from the mean and then normalized by their own standard deviation. So this is like one standard deviation above mean, one standard deviation below mean. So these are like the flood years, and these are like drought years, and it has a sort of multi-decadal variability, and these are sort of known things about monsoon. But the trend was not being estimated correctly for a long time because it depends on how much data you have. So you need a longer data to do a correct estimate of the trend. So after a lot of studies, we have estimated that it increases. The monsoon seems to increase by about 3.95% per degree. 1 degree increase of global mean temperature increases amount of monsoon rainfall by almost about 4%. But the moisture content has increased by 7%, but the monsoon does not increase by that much. So that is due to the dynamics. But this is important that monsoon does increase, but by about 3 to 4%. But most importantly, what is increasing more vigorously are the so-called extreme events. These are the sort of different percentile events which are contributing to the so so it is this indicates that the heavy events have become more and more frequent in the recent years. And these we published a few years ago in a paper in Science, and it showed that if you take the 4 most intense events in the whole central India, count just in the season, you take the heaviest events and take 4 of them and take average, and then go for all the and from 1950 onwards you take every year and do that. It turns out that the intensity of these highest events also has increased significantly. In fact, it has increased considerably from about 180 millimeter to about 260 millimeter. So that is significant. We also saw that the heavy events, which is more than 10 centimeter per day, have increased significantly, but the low and medium events have decreased. And similarly, the heavier events like 15 centimeter per day have increased at a rate even higher. So these had indicated even 15 years ago, we predicted that the extreme events are going to cause increasing flood events and plus flood events, erosion and landslide. These are going to increase. And in fact, that's exactly what is happening today. And we need to prepare for it. So the frequency of occurrence of these events, we have estimated that actually in the recent times, they have occurred, the very heavy events have occurred 3 times compared to about 50 years ago. So that is pretty large. And similarly, the intensity of the events have increased almost 21%. So this is much larger than now. Intensity is increasing much larger than the Clausius-Clapeyron, which is that 7% per degree increase, but it is 3 times that. That is more. So intensity of the events increasing means your severity of the flood events are going to be more, and so the severity is going to be increased much more. So we need to just take care of that, and that this is on a country-wise level. So I don't want to read this all, but this indicates that our frequency of occurrence of the hydrological floods and are going to increase. Not only that is going to increase, but their intensity is also going to increase. Therefore, that is a much serious condition. So we have to prepare for that. Also, the frequency occurrence of the light events are going to decrease. Therefore, the recharge capacity of the land or recharge of the groundwater is going to be more and more difficult, because more heavy events will run off faster and therefore not going to recharge. So that is also a serious problem. So we need to. In terms of the we repeated the same thing in the Northeast, because Northeast is a little bit different. Northeast, within the monsoon region, the Northeast, we found that Northeast, there is a lot of problem with the data, because Northeast region doesn't have enough data. Even IMD doesn't have enough data for a long time. So we had to collect a lot of data from various stations, in several stations. For 24 stations, we collected about 90 years of data, daily data, and from there we could find out the extreme events trend better. On the larger scale, the total quantum of rainfall we found is actually decreasing. In contrast to the central India or the rest of India, Northeast India mean rainfall is decreasing by about 3.2% per degree. On the other hand, extreme events are increasing. There is no doubt. Extreme events are increasing both in central India as well as in Northeast India. But their intensity increase is slightly less compared to central India. So this makes Northeast India quite vulnerable, because mean rainfall is also decreasing, and therefore we need to take more care. So one point I want to make at this point is that the climate science, because of the complexity, the deterministic value of any impact is very difficult to give. We have to give a probabilistic value because there will be always certain amount of uncertainty because the models cannot become perfect, cannot be perfect. But today, because with the computers available and the models, better and better models, we can do multi-model ensemble simulations and give a very good estimate of the probability of occurrence of something, probability of an event, probability of an impact, and these can be given with very high confidence. And all decisions must be based on this probability, because many of the skeptics' argument is that, well, there is a range of things that happen, so how can I take decision? But this is all nonsense, because we always take decisions on probability. Even in market, you do take decisions on probability. But when it comes to climate change, they don't want to take decisions on probability, and this is hypocrisy. So we have to overcome that, and therefore we have to convince the policymakers that we have to take decisions on these. Some of my personal thought about how to mitigate this is that obviously emission must be cut down drastically, but we must remove. I think something that people are not talking about, but without which we may not be able to really control, is that in energy demand, which actually drives the emission, energy demand must be reduced and cut down. If you continue this energy demand and increase the energy demand, and it is not supplemented by new innovations, which will completely replace by renewable energy or artificial energy or whatever you can think about in a very, so those innovations are not happening, and we are not cutting down this demand, and we are actually using energy for things that we do not need. For example, I personally believe that last month there was, or in August, we had this big news that 2 billionaires have gone to space and come back using their own private spaceship, which made a beginning or starting the beginning of the space tourism. I want to ask, do we need space tourism today? I don't think we need space tourism and waste energy. This is the wastage of energy. So what we need is cut down energy, and to cut down energy demand, unless we do that, with the growing population, we will not be able to have a sustainable solution. The research and innovations must think about very in very innovative way to find environmental source of energy, environmental friendly source of energy, and maybe artificial energy. Recently, there was some news that petrol has been produced synthetically, and if we can do that, maybe that will replace some of that. Things like that. Also, maybe for transportation, we have to think about like sci-fi movies. We have to think about certain spacecrafts which can, I mean, these aircrafts which will require very little energy or very different energy, and small aircraft, and remove all the guzzling vehicles, so that energy demand really goes down. So innovations are required there. So to help this, we all have to actually remove. We have to change our lifestyle, both private and public lifestyle. I personally believe that the private jets for anyone should be abolished. Helicopters and jets for electioneering should be stopped. So I think these are the things that, these are sacrifices we have to make. Without doing these sacrifices, I think the next generation is going to face a hell rather than live in a Goldilocks planet. So this is my, so the point that I want to make, last point, I think, how much time do I have? Sumit?
Sir, you still have lots of time.
Okay, no problem. I'll finish in 10 minutes. I'll finish in 10 minutes.
No issue, sir. We have time up to 1:30, 1:40. So please take your own time.
No, I don't want to, because I'd like to have some questions if necessary. Okay. So the next point, the problem I want to just highlight, this is, I'm not going to go into detail, is that the flood, the living with flood. I feel that the flood in the Northeast is a very serious problem. Every year we have this problem, and this flood in the Brahmaputra basin, where people becoming more frequent and more intense, and this is causing a lot of hardship for a very vulnerable set of population. The people who live in the villages are poor, they and this is causing a real hardship. But what I'm not seeing today is that there is no. Today, I think with the technology that is available, the models that are available, data that is available, their precipitation forecasts have become better. Combining all these, I think we can make a very much better forecast of the floods 24 to 48 hours in advance. And if the flood forecasts are better, then the evacuation and of the people from flooding areas could be more effective. And together with that, if we could build shelters like cyclone forecasts. The cyclones today, tropical cyclones in India has saved, tropical cyclone damage have been controlled significantly in India because of two things. We have improved the cyclone forecasting. Cyclone forecasting over the last 15 years have improved so much that now people believe them. When they believe them, the disaster management authority have been more effective in evacuating people. But side by side, we have been building a lot of shelters. Now, once the shelters are there, people are evacuated to the shelters, and the human loss is minimized. So even in the most category 3, category 4 cyclone, we have very little human loss. And these we have been successful. I believe that the same can be successful. The same model can be used for floods in Assam. So we can produce a better flood forecasting model, and this flood forecasting model can then give forecast early warning. But together with that, we have to build shelters. Today, what we are doing is mostly in the Northeast. Basically, it is a flood control strategy. You being embankments. These embankments are built wherever there is a possibility of flood breaching, and therefore these embankments get washed out during the flood period. Again, next year you build. This is a useless strategy, and this is going on for 700 years, but we have not been able to help people with that. So I believe that we need to go beyond that. Of course, there are challenges, but the challenges are not surmountable. And the Brahmaputra itself is a challenging river. It has 40 plus major and minor tributaries. The terrain is very complex and very steep. As a result, the flow velocity is quite strong. That flow velocity actually produces a lot of eddies, and they produce erosion. The erosion is also very important part in this Brahmaputra. And together with flood, in fact, we have to do the erosion forecasting also. So that is a different issue altogether. But now the flood forecasting can be done because there are people who have already done some modeling of this. There are expertise available. The floods are actually very episodic. There are certain interesting that in this is different the monthly rainfall, and the floods comes in sort of waves, and these seem to be associated with monsoon active and break conditions. So there is a sort of monthly time scale. Almost every month there is a flood episode, and this is a large scale flood. On the top of that, there will be also in the tributaries, and there will be flash floods where there is concentrated rainfall. So we have to take care of both. And I think one can develop, following the same strategy from weather prediction. I can see that we can have a larger scale model which will make forecasting on a larger scale. But then you have a regional scale, smaller scale, more high resolution model to produce the flash floods within that. And these all that can be connected to. So there are expertise. In fact, Dr. Subhasisa Datta and his students are doing some good modeling work at IIT Delhi, IIT Guwahati, and I think there are expertise here. It's not that expertise is not there. What is missing is that validation. I feel that there is some people are doing regular flood forecasting, but I am very not convinced that they are good because they have not been validated properly. But therefore, the bad forecasting or unvalidated forecasting are useless to the society. They can be simply people who don't know anything about the floods. They may be okay to show pictures that there is a flood. I am giving warning here, warning there on that. But ultimately, they are of no use. So, but therefore, any forecasting has to be validated properly, which has not been done. So, but it can be done today because we have good data, but the validation data is a little bit of a problem, and so therefore there may be a need to develop or generate a certain amount of validation data at different places in the domain. That may be part of the project, and this can be done. It is not something that can be done. We have now trim data to sort of test the hydrological model, then validate them with and fine tune with parameters, and then forecast it, and finally you can combine them, test them back with observations, and then and see what are where we are missing, and then sort of improve the model. So there should be a strategy of how to develop a model, test it, and again feedback to the improvement of the model. And that is, I think, quite possible because my experience with weather and climate forecasting, I see that it is possible, but it's not being done in a comprehensive way. And that is what I think needs to be done. The validation data is a problem because there is not enough research data available on a day-to-day basis, a number of places that is required. And that is something that should be generated. And one experimenting for a couple of years can really do a good job of doing collecting this data, and that should also be done. Now, if that is done, then you have these operational model. So this should be on an operational basis, and during the monsoon season, from May to October, we can have run this on operational basis and give the forecast. And if there is places where you can give proper forecast, and then the evacuation can be tourist shelters can be activated, and these building of elevated shelters is a key thing to that. And I think that this can be done at the same cost that we are doing the embankments, and is not a very different. It's a change of strategy that we need. Of course, the last thing that I want to mention is that I don't want to go into details, but one in the Northeast India is also a very important biodiversity hotspot, and there are very several things in this region. That's like the very unique Muga silk, for example. It happens only in this region because of the high rainfall, high humidity, and the temperature. And this is a very unique climatic zone for which there is unique ecological services that is available. For example, Muga, Eri, and others. So livelihood of many of these indigenous people depend on these ecological services, and climate change is definitely affecting them significantly. But there is no good quantification of these data. There is no baseline data on any of these. Similarly, there is no modeling studies to test how we can actually help these cope up with this climate change. So there is a lot of work that is required on biodiversity and the impact of climate change on the Northeast biodiversity. Very little work is done, but I have done some literature survey, but I find that very little work is done, and that is what concerns me. We need to do a lot more. So one thing we can do is to actually start with a conversation with biologists and ecologists, and then write a white paper of what we know and what we don't know. And then some experiments can be monitoring of natural system is required. So some of the things that what is happening, unless you have the baseline data, we may not be able to really get any estimate of the climate change impact on this. That baseline data is not there at all, and so we must start doing that. But you can also do side by side certain controlled experiment, field experiment to estimate the climate change. There is also one simple thing that we can do is kind of look at from the people like your center. People have done a lot of what you call the remote sensing work. And one thing is that climate change is, of course, affecting the basic primary productivity itself. And these primary productivity can be estimated from satellite observations of at least last 20 years or so. That from that see whether there is a trend or not. This has been done in some parts by some people, but not in the Northeast. And I think this is something that that needs to be done in the Northeast immediately. Somebody can do this, and then you can actually look at least what is happening to the primary productivity. Then we go down to other important ecological problem. So with that, I think I'll stop here, and we'll be happy to entertain some questions.
Thank you very much, sir. It was a wonderful lecture, and the lecture that was having elements almost for all category of audience that we are having today.
Okay.
You can have a glass of water, sir. In the meantime, I'll look at the chat. And I also invite all my students to, come forward, ask questions, ask your doubts rather than questions, and we have with us Dr. Goswami to answer your questions.
Sure,
So
sure.
feel free, please feel free to ask the questions.
Can I ask one question?
Please,
please.
I will be happy if you can show your face and introduce yourself very briefly.
Yes.
Very briefly.
Yes, sir. Yeah.
Okay.
Yeah, I'm Ajanta Goswami.
So, hi.
Sciences.
Hi. Thanks a lot for this wonderful lecture. It was really enriched with so many elements. So my question is, previously we discussed regarding your work on thunderstorms and lightning. So what exact progress is done in that particular field? Because we from our center are also looking for some prospect on that particular field, working on lightning.
What do you mean by progress? In the sense that today we have, of course, one of the issues of the lightning is there are different aspects of lightning. Of course, there is issue of understanding why there is difference in the lightning over in Northeast, for example, and why the lightning characteristic in the central India is very different from that in the Northeast, and why it is so. It might depend on the microphysical processes and the CCNs, so therefore that's one issue. But of course, the lightning forecasting is another issue. We have not done any work so far in the Northeast on the lightning forecasting, but some of my colleagues at IITM are doing on forecasting. Now, lightning monitoring is another issue, which is already some progress has been made on lightning monitoring, because lightning, of course, affects, lightning deaths are there. To avoid lightning death, if we can predict the lightning cannot be predicted too long in advance, but at least nowcasting you can do. Nowcasting about 1 or 2 hours in advance, we can say that this is the place where we expect more lightning to happen. This can be done by simply monitoring. That is a new monitoring network has been set up in the Northeast, again from IITM in collaboration with NESAC. they have put down a new a monitoring network. So that's all that's happening. But what is still not don't understand, and of course in several other parts of the country also, lightning monitoring network is improving, is becoming better. Maharashtra is there now, Andhra Pradesh is there. So several parts of the country now, there are more dense lightning network. So these lightning networks are helping us to monitor it better. But lightning can be also there is other lightning sort of amount over the season. So do we expect more lightning this year or compared to that year? This kind of a forecast also is required. So that kind of a thing some people at IITM doing by associated with seasonal forecasting. So this because they depend on mainly on the synaptic activity. Suppose the synaptic activity we can predict, the mesoscale activity we can predict better, and then the model will be able to also predict the lightning. So therefore, there is some element of that going on. But the crux of the problem is that in all these, there is a lightning parameterization that is required, which is where work is still needed. It's not very, it's only preliminary. So how lightning actually happens within the model. Model does not have a real lightning model. Lightning model, what models have is produces from the convective parameterization, it produces a raindrop size distribution. So from the raindrop size distribution, you have to say that if I have this kind of a distribution, how much lightning and what type of lightning we are going to get. So this is the lightning parameterization. Lightning parameterization today is very, very still primitive. It is not very, very, very sophisticated, and that is where a lot of work is required, and is still not enough.
Thank you, sir. Ajanta, anything further?
No, thank you, sir.
Good. I think Sumit has raised his hand. So please go ahead, Sumit.
Yeah. Thank you, Professor Arya, and thank you, Professor Goswami, for a nice talk.
Thank you, Sumit.
Picking up the caution, what you basically at the later stage of your presentation talked about, we have a good satellite-based precipitation products now, like TRM.
Right.
Now we have good models also developed for flood estimations and flood modeling. Now, the part which you are mentioning that it is not coming out very strongly is, let's say, validation. But I'll pick up the Northeast region only, and I'm also sitting in the Indo-Gangetic region. We know because of the climate extremes, we are facing flooding and lots of extreme events coming. Because both these systems are classified data in terms of discharge. So how do you suggest to our students to overcome that problem? You know, like it's a classified data. We do not get easily the discharge data. So how do we expect the models to be validated?
Yeah, I think there is some ground truth is definitely required. So some experiment, you don't need a long-term experiment, but you need a few years of experiment, like 1 or 2 years, a continuous experiment in a fixed few points, like that you need, so that at least you have a validation. So and then there should be certain monitoring points, few monitoring points, increased number of monitoring points. Now, my problem is that CWC data is not only classified, so-called classified, it should not be classified. In my opinion, they should be declassified. Secondly, they are also not very well calibrated. So therefore, I am sometimes not even sure their data is good. So I think there is a need for a series of research quality or quality data for a period. It may not give you a forecast validation, but at least you can validate the models. You have to validate the models. To validate the models, you have to have at least some data where you can actually validate. For those times you predict And if you have enough events, then it gives you statistics where the skill of validation. To do that, at least a couple of years of data over several points should be done. Both in second, it must be complemented with now satellite data. Now slowly the satellite big rivers like Ganges and Brahmaputra, I think the height could be monitored now with altimetry data, some more accurate altimetry. Not for very small rivers, the tributaries we can't do, but I think we can still do. So there is this how to you have to do research to how to bring out that signal, how to use or improve the altimetry to do that. And also from whatever altimetry data that we have, how can I get a signal out of this in a river basin like so even if I can get there are these big episodes, large scale episodes of floods. These are happening every month, especially in Brahmaputra. So these episodes also, if we can predict, you have done a big job, because that is very important, because it affects a lot of people. So in between, overimposed on that, there are these smaller episodes of smaller floods which are coming from the tributaries. So that maybe may not be possible to do with satellite, but I think with satellites we can still do. I think people are some. I'm not yet up to date into how exactly, but I have a feeling that this could be done and this should be explored. Or we should explore some monitoring altimetry studies, even aerially measured like LiDAR or other things. Some measurements you should make with drones and LiDARs and others, drone measurements, so that we can make extensive measurement using other aerial methods, so that we have it's a set of validation data, and that is very important. That is also, I think there are other alternatives that not just satellite, but other aerial platforms that we should explore, where we can get more data, validation data on the sea, water level.
Thank you, Professor Usman.
Thank you, sir. In the meantime, I'm waiting for more questions. Can I also ask some clarification, sir?
Sure.
So one day in one of my class, there was a question, and it was a very simple question, but it was unanswered on that day. What causes the seasonal or annual variation in the concentration of CO2?
Well, I'm not an expert, but that is, I think, not in a given place. So the annual variation depends on where you are. Suppose CO2 is very well mixed. Now, suppose you have even the polar region. Suppose in Antarctica, if you look at the time series, there is very little annual variation. There is no variation, almost smooth. So Mauna Loa also, if you see, that is a very pristine region. So there, the annual variation is there. That is very small. But when you come to sort of habitated region like here, anywhere here, the annual variation will be very large, especially in the extratropics. That annual variation, suppose where the trees shed leaves in autumn, and then winter is completely bare. So that time there is no breeding. So so they don't take in carbon dioxide. So there is no carbon dioxide intake. On the other hand, in the spring and summer, a lot of carbon dioxide is taken out by the trees, and therefore a lot of carbon dioxide from the local region goes into the carbon sinks, and therefore it decreases. So therefore, breeding in and out by the vegetation in a vegetated region, and if there is a seasonal cycle of that, which happens to be very prominent in extratropics, there is the annual cycle is large. So the annual cycle over a vegetated region in anywhere, for example, if you take somewhere in United States, in any of the places away from the cities, little bit away from the cities, if you take, there will be a lot of trees, and then the annual cycle is very large. On the other hand, in the tropics, the annual cycle will be slightly less, because we are evergreen. So there is the vegetation is there all the time. So therefore, the annual cycle is still small. But this will be still, it will take a lot of, it will be different from the ambient carbon dioxide, because there will be large amount is already, if you have visited the region, it is taking in a certain amount of carbon dioxide. So it is our data may not be able to, if you make measurements here in a location where there is vegetation which is perennial, then you cannot get the ambient background assessment. Therefore, you have to go to a very pristine region. So go to Ladakh or somewhere where there is no trees. Then you will get, time series will give you only the ambient. That only can compare with Manalwa. You cannot compare with Manalwa what you are doing here in any other places because of the trees, because of the perennial trees. So it is basically the vegetation breeding in and out makes a annual cycle. The annual cycle could be subdued in the tropics because of perennial trees, but this will always then be lower than the ambient well mixed carbon dioxide which you can find in the atmosphere. Everything gets mixed up, and then you have a background which has to be measured in a very pristine place in the tropics.
Thank you, sir. Sir, there is one more clarification. As a hydroclimatologist, I am really interested. Like in one of your slide, you have said like high level clouds and low level clouds.
Right.
Have different reflective and emissivity and absorption properties.
Right.
Is there any, what causes that difference between low and high level?
Okay, the reason is that that the high level clouds, so you see that sometimes we have these cirrus clouds which are hanging out in the upper atmosphere. Those cirrus clouds have ice crystals. Okay, they have very little, they have a lot of ice crystals, but the water is also super cold. So, but they are not very thick. So since they are not thick, and their concentration is not very high, and even if they are high, because of the ice crystals, the sun rays goes through it. Now, but because they are layered cloud, so the long wave radiation gets absorbed. Long wave radiation cannot go, even if it is transparent, like a glass. So transparent glass also does not let long wave radiation go down. So that is why there is greenhouse effect is strong, but reflectivity is low because most of it goes through it. On the other hand, low level clouds are more thicker. The raindrops are thicker. So the thick raindrops make more reflectivity. So it reflects if the concentration is high of bigger drops, and these bigger drops have collectively have larger reflectivity, and they are bright. So that makes it more reflective. But because they are closer to the Earth, the amount of long wave radiation that is absorbed tends to be small.
Thank you, sir. Sir, I think I am getting chance to ask one more, and my last clarification. I'm really curious to, rather I'm tempted to ask this question,
Tell me.
Still, I don't think, is there any question from other student or audience? Yes, Sumit, please go ahead. I'll ask my question.
Professor Diman has wrote a question. So
okay.
Asking
Professor, please read it.
Yeah, Professor Diman, can you unmute yourself? Yeah.
Okay, sir, good afternoon, sir.
Good afternoon.
Sir, I have a very simple question from my point of view, but yes. I understand that there are several dimensions in the climate change. So, yes. Because as I said, several dimensions in the climate change, but I want to know that one or two important new suggestions for the new generation so that we can do the modeling of the climate change. One or two important suggestions from your side.
that's a rather broad question in the sense that modeling the in India, we have been lagging in modeling in terms of climate change modeling, if you call it. So that has been now started, but we are still in the early stage. So I started this climate Earth system model at IITM, and for the first time, so we need a Earth system model to do any sensitivity study for these climate change science, and we need to do also a lot of physics sensitivity studies, so that the uncertainty can be established there. Because as I said, because of the complexity, there is a certain amount of uncertainty. To reduce the uncertainty, we need to do a lot of sensitivity studies. So, but to do that, you need an Earth system model first. So the Earth system model was not there in India. So for the first time, we had done that in IITM few years ago. And now that model has now contributed to the 6th assessment report. So in the CMIP 6 models, there is an IITM model today, India's model. So that model gives us what will happen to if we double the carbon dioxide, or what will happen to the Indian monsoon if under different scenarios, the SSP 4.6, SSP 8.5, etc., etc. So this is one part of science. Now, once you have that kind of a model, then you can use that model to look into various aspects, like you have to first establish sort of what kind of confidence I can have into these projections. So that confidence now we are now building up using not just one model, but maybe using other models from other scientists, and so that you can reduce the uncertainty and then use those data to use impact studies. Impact studies can be done on you don't need all that, but you need reliability of the projections. So that I see a lot of impact studies in the country, but those impact studies do not essentially take into account what are the kind of uncertainty there in the projections. So we have to. So therefore, especially for Northeast, the impact on the Northeast, the simulation by almost all climate models is rather poor in the Northeast because of the orography. Because orography is rather mesoscale orography. It varies over 100 kilometers, and most of the models have low resolutions. Even the Cordex model, which is a regional model, has an average resolution is about 50 kilometer by 50 kilometer. So these models do not represent the orography in the region correctly. Therefore, underestimate the rainfall. So now, and overestimate the temperature. So therefore, what happens is that now if you use those output from these, even the regional model data, and look at the impact on future, I think we are going to have a lot of error. And these are the things that we need to reduce. To do that, what we need to do is to improve simulations in certain regions better. So use regional model of higher resolution to mean climate. Central India is okay because Central India doesn't have too much mountain. So therefore, some of the estimates are good. But in Northeast, we cannot rely on them. But many studies have used them and they have made a lot of conclusions. But I cannot trust those conclusions, right? So these are the things that we need to do carefully. So depending on which region you are, you must check what is the climatological simulation of the regional model. If the climatological simulation of the regional model has large bias, then the projections cannot be trusted. And then you have to do something. You have to either improve the regional model, and so that you have at least a reasonable, reduced bias, so that you can trust some of these projections. So these are some of the issues. There are many issues like that. There are a lot of science issues that we need to work on. And regionally, it is the regional impact study is one of them, and which is I think not done quite satisfactorily so far.
Thank you, sir. Professor Dhiman, any response, anything further?
No, I think it is enough for me. I think.
Thank you.
Thank you very much, sir.
Thank you.
So we have a question, and can you read the chat, or should I read it for you?
Can you read it? I think
Saurabh is our student, master's student, and he's asking how global warming is affecting Indian oceanic dipole, and so since we also know that these are natural phenomena.
Okay, that's a very good question. Well, actually, I don't have a very good answer for that. There is a lot of studies on El Nino and what the global warming will probably do to the El Nino. But there are not enough studies to really quantify what would happen to what is expected to happen to. There are several studies, but those studies are not conclusive in my opinion because of two things. Because most of the models have difficulty in simulating the IOD and global models, and so therefore the conclusions they make on that has to be taken with a pinch of salt. So therefore, I would not really conclude so much on what are expecting. Already we are there is a tendency for IOD to be more frequent in the recent years, which already is a part of global warming. So we might expect that maybe IOD will become more frequent in the years to come, so because due to the global warming. Because over the last 100 years, especially over the last 50 years, Indian Ocean temperatures has seen a very strongest rising trend over the world. Therefore, this is partly due to global warming and partly due to certain natural oceanic processes. As a result, I think it is a kind of surrogate effect on whatever happening in the last 50 years to the IOD from observation gives you an indication of what we might expect to happen. And one thing that seems to be happening is that IOD seem to be more frequent in the recent years. So that is probably what I would expect. But as I said, this is still early days in terms of reliability of these predictions. So we need to or the projections. So as far as ENSO is concerned, ENSO is considered to be more going to be intense, more intense in the global warming under scenario, and that is something that is also I think that part is relatively more. There is more data, more model, and ENSO. Most of the models do reasonably simulate ENSO, so we have a little more confidence on that.
Thank you very much, sir. Sir, I think we have come to
Okay.
time when we have to close. But before that, if you allow me, I would like to ask one last question from, or rather clarification from my end.
Okay.
Sir, as you very well know, India is an agrarian economy, and our main thing is based on agriculture. And agriculture here is based on monsoon. And so my precise question is, what is the future of monsoon in 2050? Will it be the same? Will it intensify? Will the mean rainfall is going to change everywhere? Will the extreme change? How it is going to be? How this we will look at in 2050?
2050 is a little bit far away, but I think the general idea is that our as I have said, the two results are pretty well known. One is the mean rainfall is expected to increase at the rate of about 4% per degree increase of the global mean temperature, and I am expecting that by 2050 we will have almost 1.5 or 2 degrees increase. So,
yes,
so because I think by 2050 we are almost going to touch 2 degrees. If not, so if you have 2 degrees increase, which the models are predicting today, most of the models, and the scenario is not changed, and then we might have at least 1.5 degrees. So if I have 1.5 degrees, conservative estimate is that we will have about 6% increase of total. So today we have 850 millimeter. So 6% increase of mean rainfall you can expect. But more importantly, that is not much. But more importantly, by 2050, the frequency of occurrence of extreme events, rainfall events, and the heat waves. I did not talk about heat events, but heat events are equally increasing. So heat waves are also very dangerous for health. The heat events are going to increase quadrupled or even more than quadrupled in the by 4 to 6 times more by 2015. The extreme events, the 10 centimeter and 15 centimeter rain per day will increase by about 4 to 6 times by that time, and that is going to be disastrous for flooding. So, and the intensity of these events are also going to, as I said, the 20% increase per degree. So so today's events, if the largest event is 20 centimeter per day, these events are going to be almost 30 centimeter per day by then. So that is going to make a very big difference in terms of hydrological disasters. So people used to think that this is where the problem is. People think that many meteorologists actually argued that, well, global warming has a good effect because monsoon is going to be more strong. But monsoon strong is not going to help us at all because the extreme events are going to kill everybody, because they will flood the urban regions as well as the rural regions. Both places are going to be affected, and they will affect the food production because of floodings and property loss, human loss, everything will be increased by several fold. So I think that is what we need to focus on. And this data is already there. You can project it today. And based on that, you should be able to make decisions that how should we cope up with it? What kind of preventive measure we should take? And this is the time to do that today. And this data is, I think, quite robust. I think now our work has shown how the global intensity of the extreme events are increasing, and how much temperature is going to increase by 2050. I mean, is also pretty good estimate can be made from the modeling studies, and using these two you can make a very good should be able to make a good plan for adaptation strategies. And
yes, sir, please go on.
No, that's all.
Sir, I take away this point from this last clarification that the extreme events are going to increase. This increase in the total rainfall will be in terms of these extreme events. Right. And if that is the case, then the role of the students having, who are studying here in our center, taking masters, their course, studying how to manage disasters is going to be, more and more in coming future.
Correct. You have to think about it. Yes.
Yes. So thank you very much, sir.
Thank you
for enlightening us. Now I'll request Professor Ajanta Goswami. Professor, are you there?
Ajanta? Yes, I'm here. Yes, sir.
Request Professor Ajanta Goswami to come and show our gratitude to Dr. Goswami. Sir, thank you very much. Over to you.
Thank you, Dr. Arya.
Yeah.
My pleasure, sir.
So it's my thank you so much, sir, for being here and delivering such an excellent lecture. And I think we all are inspired, and maybe many of us will take up some interesting projects on Northeast India, along with your guidance. So I think we all are interested. Amit is there, Arya sir is super excited, Sumit is there, Subir, he is an economist. So like we have got a different expertise here. MS Sharma sir, he was here recently. Now I think he has logged off. So he's working on earthquakes. So we have a very good expertise here, and we all can work together and bring up some really good project, meaningful project, which works on for Northeast India. So thank you so much, sir. And we hope that with this lecture, we'll continue our relation for a long time.
Sure, sure. I'd love to keep in. Thank you so much. Thank you all.
Thank you, sir. Good day.
Okay. Okay. Bye.
Bye.
Bye. So yeah. Sumit, so should I continue with the, yeah, so I think, yes, we appreciate the effort of all the students as well as the organizing team. Organizing team means all of us from the COADAMM for all the nice efforts and bringing up all the good people and listening to their lectures. We will be meeting again at 2:45. And for the JKML lecture, and I hope that we all will be here and we will attend that particular lecture, and then we will have a combined vote of thanks for all the events. So thank you so much. Yeah.
Okay. Thank you. Thank you very much.
Thank you, everyone. Thank you, Professor Arya. Thank you.
Thank you.
Bye, Sumit.
Dr. Dhiman. Thank you.
Thank you so much, Sumit. Thank you.
Yeah, we'll look forward to see you all at 2:45. Sorry. Too busy.
Bye.
Yeah.
Yes.